Wanted to work through the worksheet that was for our first recitation. So this is a worksheet in which we haven't met any material in electricity and magnetism in Physics 213. Really, it's a worksheet to remind us of some of the material from Physics 211. It's material from Physics 211 that we're either going to use a lot in Physics 213, or it's material from 211 that parallels work that we're going to be doing in Physics 213. So the thing that we're going to use a lot in 213 that you also used a lot in 211 is vectors, is addition of vectors, is working with vectors. The thing that has a parallel with what we've done before in Physics 211 is working with electrical forces and electrical energy. We're going to compare that, we're going to parallel that with working with gravitational forces and gravitational energy. So the first question on the worksheet asks us to think about two forces that are acting on a block. Think about the addition of these two forces that are acting on the block and the resulting, the net, the total force that therefore acts on that block. In the first part of this problem, we've just got to sketch the forces that are acting on the block and sketch the resulting total net force. In the second part of the question, we've got to get more quantitative, more precise. We've got to calculate the magnitude and direction of the resulting force from knowing the magnitude and direction of the two individual forces. So, sketching the forces and sketching the addition of the forces. I've sketched here the block, and we're told that there are two forces, F1, F2, that are acting on this block. We're told that the force F1, that's acting with a strength, size, magnitude, 12 newtons, and is acting horizontally to the right in the positive X direction. So that's the first force. Second force has a strength or a size of magnitude that's 16 newtons and is acting above the horizontal, 30 degrees above the positive x-axis. So to the right and also up. So I've drawn the block here, and I'm going to add to the block. I'm going to add the sketches of the two individual forces, and then we'll add the sketch of the resulting force. So here I've sketched, or tried to sketch, the two individual forces. Remember, F1 is the smaller 12 Newton force and is directed towards the right along the positive x-axis. So I've drawn that, I've indicated that with this little force arrow here. Force F2, that's the larger of the forces, 16 Newton strong, and it's directed towards the right, but also up. It's directed at an angle of 30 degrees, I'll mark it here, above the horizontal. And so I tried to draw that. We want to add to this sketch the resulting force. Before we do the calculation of its size and its direction, let's just add to the sketch, the figure, the resulting force. So I can imagine doing that by drawing vector 2, F2, starting at the tip of vector F1, and then the resulting force would go from the tail of vector F1 to the tip of vector F2. And so that's exactly what I'm going to draw. I'm going to redraw the second vector, redraw it over here in magenta, and I'm redrawing it in a way that I'm picturing adding this second vector to this first vector here. And then the resulting vector, it's going to run from the tail of the first vector to the tip of the second vector. And so this is the resulting force in magenta here, FR. I could have constructed it the opposite way around. I could have drawn the vector F2 first, and then drawn the vector F1 starting at the tip of the arrowhead of vector F2, and then the resulting force would run from the tail of F2 to the tip of F1. If I did that, I would have drawn F1 here. But either way, we're adding together the two forces. We're adding F1 plus F2 or F2 plus F1 to get the resulting force FR. And so that's a sketch of the resulting force on the block. Now we've got the challenge of calculating the magnitude and direction of the resulting force on the block. And the way that we're going to do that is using the components, the horizontal components, vertical components of the vectors to add together the two vectors. So right now, our language for the vectors F1 and F2 is kind of magnitude and direction. We've been given their size. We've been given their directions. And the language that we're going to want for the resulting vector is actually also magnitude and direction. We're going to want the magnitude of the resulting force, or the direction with respect to the horizontal of the resulting force. But the addition itself, that summing together the two vectors, we're going to do that in this language of their x and y components. So that means that we've got to first take F1 and F2, convert them into their x and y components. Then we can add them together very straightforwardly. Then we've got to take that resulting vector in its x and y components and convert it back into magnitude and direction. So that's our plan. So first step then is to write down F1, F1's x component and y component. I'll call it F1x, F2, F1y. And we've got to write down F2's x and y components. So I'll call those F2x and F2y. So F1x and F2x is actually very straightforward. It's very straightforward because F1 is simply pointing in the x direction. There's no component of it in the y direction. So that means that F1x, the x component of F1, is simply F1. And so it's simply 12 newtons. And that F1y, there's no y component of F1, and so that's simply 0. That's straightforward. That was easy. F2x and F2y, a little more complicated here, but just a little bit of basic trigonometry. F2 on my sketch upstairs here, it has a vertical component, this vertical line here. It has a horizontal component, this horizontal line here in blue. And those are these two components. They are, this one here horizontally is F2x, this one here vertically is F2y. They're related to F2, the magnitude of the force, through the sine and cosine of this angle, this 30-degree angle. If I multiply by the sine and cosine of the 30-degree angle, I'm going to pick out the x and y components. So that's all I've got to do. So F2x is actually F2 times cosine of 30 degrees because the horizontal component is adjacent to the angle. And I already calculated that, and it came out to be 13.9 newtons. And then F2y, that's going to be equal to F2 times the sine of 30 degrees because we want the side of this right-angled triangle involving the force and its components. This side is opposite the angle. And I've already calculated that, of course, and that came out to be 8 newtons. So now we're in good shape. We know the x and y components of the first vector. We know the x and y components of the second vector. Actually, all we got to do is add them up. And so that's what we're going to do in the next step. So the x component of the resulting force, I'll call that F subscript Rx. It's just going to be the sum of the two x components. So it's F1x plus F2x. If I add those together, that's the 12 newtons plus the 13.9 newtons. So it's 25.9 newtons. That's the horizontal component of the resulting vector. And the component of the resulting vector, that will be, well, we're going to call it F subscript Ry. And it's going to be the sum of the two horizontal components, F1y plus F2y. Now, F1y was actually 0. F2y was 8 newtons. And so this is just 8 newtons itself. And now we've got the resulting vector. We figured it out. We figured it out in the language of x and y components. The final step then is to turn this language for the resulting vector into the language of magnitude and direction. We're asked to figure out the magnitude and direction of the resulting vector. So let's go ahead and do that. Firstly, we just need Pythagoras. I mean, we need his theorem. We don't need him. And Pythagoras' theorem says that the size of the resulting vector is equal to the square root of the sum of the squares of the horizontal and vertical components of that vector. So that's the square root of Frx squared plus Fry squared. And again, I've already worked this out ahead of time. And if I can find my notes here, I've got 27.1 newtons. So that's the magnitude of the resulting vector. And the angle of the resulting vector, we can calculate that with a little bit of trigonometry also. To do that, we just have to remember that the vertical component of the resulting vector, well, that's this side here of a right angle triangle. The horizontal component is this side here of a right angle triangle. And together, that horizontal and vertical components of this right angle triangle with the resulting vector make up a triangle that has an angle in this corner, which is the angle, the direction of the vector. And that's what we're going to try and find out, is theta here. And so theta equals by trigonometry, using the tan function, inverse tan function, is going to be the inverse tangent, arctangent of the ratio of the opposite side, which is Fx, Fy, divided by the adjacent side to the angle, which is Fx. And so if I fill in the numbers for the x and y components, this should have been Fry. I'll call it Fyr. This should have been Fxy. Sorry, if Fxr, I'll put in an R here. And if I fill in the numbers, so I'd be filling in 8 newtons divided by 25.9 newtons, I got an angle of 16.4 degrees. And so that's the angle in this corner here of this right angle triangle that's made for the resulting vector. Anyway, that's my solution to this problem. It was a problem of adding two vectors. It was adding two vectors that weren't simply parallel to one another or opposite to one another or right angles to one another. It's a bit more complicated, but not too complicated. To add these two vectors together, we took their magnitudes and directions and broke them down into x and y components. we were then able to simply add up their X and Y components. And then once we got the X and Y components of the resulting vector, we could simply change that back into the language of magnitude and direction using Pythagoras' theorem, using some trigonometry, using the inverse tangent function. And that was my procedure. And we met that, or you met that, in Physics 211, and we'll all meet that in Physics 213. It's a very important tool for us to be able to add together forces and find out the resulting force. Okay, second part of this worksheet is about gravity. And this second part of the worksheet about gravity is because we're going to be talking about electricity, and there's some parallels between gravity and electricity that will be helpful, useful for us to remember, to recall. In this particular problem, we're told that we fire a bullet from a gun. We're told that the mass of the bullet is 30 grams or 0.03 kilograms. We're told that the speed, the initial speed of the bullet from the gun is 800 meters per second. We're asked to imagine that we fire the bullet from ground level and that the bullet travels upwards, at least initially travels upwards, and it reaches an additional elevation of 22 meters. So it's fired from the ground, and the maximum height above the ground it gets to is 22 meters. We're told to ignore air resistance. We're not going to worry about the air drag, the air resistance on the bullet. We're just going to be thinking about the action of gravity on the bullet. So the first part of the question says, and I'll just talk about the first part right now. First part of the question says, using the concept of energy, using the concept of energy conservation, we calculate the change in gravitational potential energy as the bullet travels from the moment it's fired to its maximum elevation. Can we calculate the change in the bullet's kinetic energy, energy associated with this moment, between the moment the bullet is fired and leaves the gun and the moment it arrives at its maximum elevation? So we're going to calculate two changes in energy here. Calculate the change in the gravitational energy of the bullet. Gravitational energy has gone up as the bullet's now at a greater elevation above the ground. We're going to calculate the change in kinetic energy of the bullet. The kinetic energy of the bullet has actually gone down by virtue of the bullet going higher to a higher elevation above the ground, by virtue of energy conservation. We can't create new energy. We can't destroy old energy. We must conserve energy. So we're going to calculate these two changes. And actually, it's pretty straightforward. It's pretty easy if we remember an equation for the gravitational energy of any object, like the bullet, above the surface of the Earth. And we remember that energy is conserved, so that if we increase kinetic energy, we would have to decrease potential energy in this situation. Or if we increased potential energy, which is the case here, we'd have to decrease the kinetic energy. So the change in gravitational potential energy, I'm just going to write it as delta for change, and then gravitational potential energy, the change in gravitational potential energy. If you remember, doesn't matter if you don't, but if you remember, it's mgh, the mass of the bullet times the acceleration of gravity times the this would be the change in height here, the elevation from where the bullet is fired to where the bullet ends up going. Well, we know all these numbers. We know the mass of the bullet is 0.03 kilograms. We know the acceleration of gravity. We'll never forget that number. It's 9.8 meters per second squared. And we also know the change in elevation of the bullet. It from the moment it's fired, the ground level to the highest point, that difference is 22 meters. And so the change in gravitational energy gravitational potential energy is just the product of these three numbers. And I've already figured that out. 5.9 joules. It's an energy. Energy is measured in joules. It's 5.9 joules. It's positive 5.9 joules because there's a greater amount. There's an increase in gravitational potential energy. And we'll meet a mirror equation to this, a similar equation to this, when we talk about electricity. And that's why we're talking about this context of gravity. Now, we want the change in the kinetic energy. Well, this is where energy conservation comes in. We kind of just created this extra gravitational potential energy out of nothing. We have to borrow it from something else. And the change in gravitational potential energy is compensated by a change in kinetic energy that's equal and opposite. And so delta Ke, the change in kinetic energy, moving energy, is equal to minus delta gravitational potential energy, the change in gravitational potential energy. And so that's not really any calculation to do now, just to observe energy conservation. That change in kinetic energy must be minus 5.9 joules, equal and opposite to the change in kinetic energy, change in potential energy. We included this in the worksheet, this use of energy conservation in the worksheet, because we're going to use energy conservation a lot when we talk about electricity, other topics in 213. So it's a reminder of the value, the importance, the significance of energy conservation. Okay, last part of the worksheet. Last part of the worksheet asks us to imagine doing the following. We bore down to the center of the Earth. We're right at the center of the Earth. We're holding the bullet. And then we climb up this hole from the center of the Earth towards the surface of the Earth, holding the bullet. And then we head out from the surface of the Earth into outer space, into deep space, still holding the bullet. And as we walk or climb from the center of the Earth, through the Earth to the surface of the Earth into deep space, we measure the force on the bullet. We determine the gravitational force on the bullet. And we're just asked to sketch the strength of that gravitational force on the bullet as you walk from the center of the Earth out to the surface of the Earth, and then out into deep space. And so we've got to draw a graph, it's going to be a rough graph, a rough sketch. But it's going to contain the main features of how that force changes as we walk from the center of the Earth to the surface of the Earth into deep space. And of course, it does change. It does change as we walk from the center of the Earth to the surface of the Earth to deep space, because the gravitational force from the Earth is changing on the bullet, because the bullet's location is changing with respect to the Earth's mass. And so I think I'll just sketch it out, and then I'll make a few remarks about it. So the key thing about this sketch is that we're going to draw a graph with the horizontal to the vertical axis. The vertical axis is the gravitational force on the bullet. I'll just call it FG. And then the horizontal axis, this is going to be our distance, or could you call it R, from the center of the Earth. I want to mark a couple of important locations. 0 here, this is the center of the Earth. This is where we bore down to the center of the Earth. And I'm going to call RE here. This is the surface of the Earth. And we're going to draw a line that sweeps from the left to the right, that represents the strength of the force as we walk from the center of the Earth to the surface of the Earth and into deep space, holding on to the bullet. And I'm going to draw it here. It will look like this. And then kind of like this. Now, I have drawn it really roughly. I drew it way more roughly than I intended to do. But it has some key features to it, and I'm going to just discuss those. At the center of the Earth, the gravitational force on the bullet from the Earth that surrounds the bullet is actually 0. There's Earth in every direction. There's Earth above the bullet's head. There's earth below the bullet's feet. There's earth to the bullet's left, earth to the bullet's right. There's earth to the front and the back. There's earth in every direction. There's the same amount of earth in every direction if you're at the center of the earth. And so although little bits of the earth create little bits of gravitational force on the bullet, the overall net resulting force of the earth on the bullet, gravitational force of the earth on the bullet, is actually zero. And so there's zero force if the bullet's at the center of the earth. As we walk towards the surface from the center, the force grows. And that's what I tried to draw here. The force growing as we walk from the center of the earth towards the surface of the earth. And it's growing because as we walk upwards, think about it this way. There'll be more earth beneath the feet of the bullet than there will be above the head of the bullet. And actually, when we get to the surface of the earth, all of the earth is below the feet of the bullet and none of it above the head of the bullet. And so we reach a largest gravitational force, largest gravitational attraction on the bullet when the bullet's at the very center of the earth. And so we see the force of gravity rise. And that's the key feature here that I wanted to show. Then we start carrying the bullet into outer space. And we start increasing our distance more and more from the center of the earth. And so the earth and the mass of the earth is starting to recede away from us. And the gravitational force of the earth is on the bullet is starting to shrink and shrink and shrink. If we take the bullet very, very far away from the earth, many, many times the radius of the earth, then the force of the earth will be much, 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 much smaller. And so that's what I tried to draw over here. The force is actually a maximum when the bullet's on the surface of the earth. And then when we climb above the surface of the earth and go past the moon and go past, I don't know what's next, Mars and Saturn and Jupiter and Uranus and Pluto, and then we're at the next galaxy and so forth, the forces are getting smaller and smaller and smaller and smaller. We'll meet a similar situation when we talk about electrical forces. And that's why I wanted to introduce this old situation about gravitational forces. Anyway, that's the first worksheet. The idea of the first worksheet is just to remind you of the few things that you've done in Physics 211 that are going to be useful in Physics 213. It was the more mathematical side of adding together vectors and picturing the addition of vectors. It was the more conceptual side of what you learned about the gravitational force, both the force and gravitational energy.